friends, how are you? In this video clip, I am going to brief you on basic part of the textile fiber that is required to understand the chemistry of the textile chemistry. That includes processing, dyeing, finishing and other things. All textile wet processing depends on the basic knowledge of the textile fiber, that is morphology. Morphology of the textile fiber. Fiber may be a cotton, maybe a linen, maybe a wool, silk or polyester, nylon, acrylic, acetate, whatever kind or regenerated fiber like lyocell, tencel, modal, whichever fiber you take, morphology is there. Like how our body anatomy is there, all skeleton, nerve system, respiratory system and other things like that, morphology is there in the textile fiber. That morphology is required to understand. Let's start. Okay, what is morphology? What is morphology? Morphology is the study of the internal structure of the material. I am not taking this definition of morphology not only specific to the textile fiber, it may apply to any things. Morphology is the study of the internal structure of the textile fiber. Okay, textile fiber. See, textile fiber, I am writing. Okay, this is the textile fiber. You see, this is the zoom version, that is zoom version of the textile fiber, cross sections. This is the cross section of the fiber that is lying horizontally. This is the axis of the fiber. For your understanding, I am showing here. Okay, this is the cotton fiber. Okay, and this is the polyester or nylon. Cotton, poly or nylon. Okay, understand the difference. This is the natural fiber. The shape of this fiber is not same as the shape of the polyester or nylon. Here the shape of the polyester nylon is like perfect shaping is there, like cylindrical shaping is there. But in case of this cotton, there is no shaping is there. It is naturally produced. The shape, the structure is flattened here. Structure is flattened here. But you may heard this flattened structure is converted into cylindrical form in the process of mercerization. Okay, that is the other part. I will come with that part. Okay, see that I will take. Just I am coming here. I will come back. Here morphology is there. In the morphology, if I keep this fiber like horizontally in this way, you think this is the direction of the fiber. Okay, this is the axis of the fiber. Here inside the fiber there are polymers are there. Polymers there are, I am writing here, there are polymers are there. Polymers. Okay, polymers are there. Polymer chains are there. Polymer chains are there. Okay, crystalline region is there. Crystalline region Okay, and amorphous region is there. Amorphous region is there, and highly oriented region is there. Highly oriented region is there. Highly oriented region. Okay, these are the things play an important role in giving shape to the fiber, giving shape to the fiber. Not only shape to the fiber, these things decide the properties of the specific fiber. Whatever the morphology is there inside, the arrangement of the morphology, the structure, the placement of these things in the fiber, that decides the physical properties as well as chemical properties of the textile fibers. Okay, any changes, any alterations, any variations in these areas, regions, that is directly influencing the fibers. Okay, here what are those crystalline regions are there? Crystalline, before that I am writing here, polymers. Polymers are the chains. Polymers are made of monomers. Polymers are made of monomers. Monomers, these chemical peoples, chemical engineering people or chemistry, BSc chemistry, MSc chemistry peoples, master of chemistry, they can understand what is monomers. Monomers are made of molecules. Monomers are made of molecules. Molecules again made up of, then if you go in deep in the chemistry, it is made up of, the things are made of atoms. Atoms are made up of neutron, proton and electron. The material on this earth start with electron, proton, neutron and made up of atoms. Number of atoms together make molecules. Molecules turn into a monomers. Monomers are linked together to make a polymers. Polymer make a polymer chains. All polymer chains are together behave or untogether behave. Together or individual or together or in group behaves. That predict the properties or features of the tissue fiber. Okay? Monomers. Here, crystalline region. I am writing here. And directly I am going here. This is one monomer is there. This is one monomer. This is one monomer. This is one monomer, 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 monomer. Okay. All individual monomers are together connecting and making one polymer chains. Number of monomers together forming one polymer chains. Okay. Here one polymer chain is there. This is one polymer chain. Okay, this is one polymer chain. 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 How many polymer chains are there? There are 5 polymer chains are there. They are binded together. Binded together by means of the chemical groups. In the polymer chains, there are hydrogen bonds. Hydrogen bonding is there, that is chemical bonding is there. Hydrogens and OH groups, hydroxyl groups will be there. Hydroxyl groups, hydrogen will be there, and other things are there. Many things are there. It depends on the chemical substance of the fiber. It may be a cellulosic substance, it may be a polyamide substance or polyester substance. NH2 or NH, like that it is there. These hydrogen bond, hydroxyl bond, hydrogen and hydroxyl groups make or NH group, whatever is their groups. That depends upon again, if we go in deep, that is we have to study as per the specific substance present in the fiber. Now I am thinking here, whatever it may be, hydrogen, hydroxyl bond or cotton or nylon, I am not taking any specific fibers. General I am talking. These all polymers are binded together, okay, with the hydroxyl or hydrogen, what binding is there, together they are making a one group, and this is one group. Here one more bonding is, here one polymer chain is there, here one 4 or 5, I am saying 4 or 5, but in the fiber, it is 100, 200, 300 more fibers will polymer chains are together making a bonding. For example, I am saying 4 or 5, but in actually in fibers 100, 200, 300. The number of will be there, number of polymer chains making here. Okay, this here, this one reason, and again here one reason is there, like this, it is lying, this is also one group of polymer chains, this is also one group of polymer chains, here also one is there, this is also one group of polymer chains. Okay, these grouped, some polymer chains are grouped together making this region. This region is called crystalline region. This region is called crystalline region. Okay, and this region is called crystalline regions. And some are there. Okay, some regions are there. Okay, this is also crystalline is there. This is also crystalline is there. This is also crystalline is there. In this type of crystalline regions, some crystalline regions are parallel to the axis of the fiber. Here you see, have you observing? Here there is an axis of the fiber is there. For this axis of fibers, this group of polymers, crystalline region is the exactly parallel is there, making a parallel to the fibers. Some polymer chains, here some polymer chains are there, that may be individual or group. Okay, they are parallel to the axis of the fibers. The crystalline regions or the polymers parallel to the axis of the fibers is called highly oriented region. Highly oriented regions. Okay, now you say, but this type of group, here one group is there, here also some polymers are together making bonding, but this group is not parallel to the axis of the fibers. But here the strength is there. Here number of polymers chains are grouped together, but they are not parallel to the axis of the fibers. But only region is there. So we can call them only crystalline regions. Now we have understood that group of polymers are called, group of polymer chains are making whatever is there, that is crystalline region, and that crystalline region, if it is parallel to the axis of the fibers, then that region is called highly oriented regions. This is not enough, but also some another reason is there. Some polymer chains are there, they are not at all bonding with any other. This is also one polymer chain, 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 this is also one polymer chain. Okay, right? They are free, these polymer chains are free from each other. They are placed randomly, in a crisscross manner. They have not in a systematically placed. The crystalline regions are highly oriented regions. For them there is a specific placement is there, but in these polymer chains there is no placement. And also you understand, the whatever polymer chains are there, here some part of the polymer chains are bonded together, and balance whatever the outcoming are there, that is also coming. Here after sometimes it is going link here, and going like this here, and going like this here. How the behavior of the polymer chains, it depends upon the nature of the productions. In case of natural textile fibers, this type of placement is possible. But please remember that in case of synthetic fibers or in case of regenerated fibers, that is man-made fibers, artificial fibers, in that artificial fibers, the man is not allowing these polymer chains to place how they want. He wants polymer chains should be parallel to the axis of the fibers. All polymers All polymers, 90, more than 80 to 90% of the polymer should be parallel. He will take care in the industry that the polymer chain should place parallel to each other. Maximum number, maximum percentage, 70%, 80%, 90%, whatever. 100% is not possible. Something is there by means of drawing mechanisms in the spinneret. Okay, that is the other topic. I will not go there. Now it come back. See, this is natural fibers. Why in this cotton fibers? Why cotton fiber is flattened? The shape of the cotton fiber is flattened. Why the shape of the polyester nylon fiber is flattened? Cylindrical form, perfect shape is there. In the polyester or nylon fibers, whatever cylindrical is there, perfect shape is there. That is, in this case, all polymers. In this case, all polymers are parallel to the axis of the fibers. That is man-made. But in case of cotton, in this position is there. This is the position. Understood? What is the difference between natural fibers and man-made fibers? Okay. And now, third reason, whatever this free, how the polymer chains which are free and moving, not moving, is how they want is there. That reason, whatever this reason is there, that reason is called amorphous reason. This is called amorphous reason. Okay, this is called amorphous reason. Now we have understood what is crystalline reason, what is amorphous reason, what is highly oriented reason. These three reasons decide the fate of the fibers, that is feature of the fiber or end use of the fibers. This part, amorphous reason, crystalline reason, highly oriented reasons decides the physical properties of the fibers, chemical properties of the fibers. Physical means it may be a strength, it may be a tenacity or tensile, whatever it may be, it is a strength. Okay, shape, color, moisture regain. Okay, moisture regain. Now I will come to that topic. I am not making this video the short video. Please, I am requesting all viewers to understand this topic. I am further extending the time of this video. I plan to take 3 minutes, but I am extending. Now already 17 minutes is over. First understand, then only you can understand the next wet processing what I am taking on reactive dyes and sulfur dyes and wet processing and finishings. Okay, now amorphous reason, if this is the total 100% of the structure is there. In this 100% structure, the content is 100% is there. In this 100% content, if 100% content, if you divide into percentage, some percentage you give to crystalline reason, some percentage you give to amorphous reason, some percentage you give to highly oriented reasons. Understand? Please have the concept. If 100% of the content of the fiber, if 33% is highly oriented, 33% amorphous reason is there, 33% crystalline is there, that type of content percentage distribution produce one quality of the fibers. That in turn produce one quality of yarn. That in turn produce one quality of the fabric. That in turn results in the dyeing or finishing or wet processing or ultimate end consumer fastness or whatever low, so on. Okay, you forget. I divide 33 divided. But first case study first. If amorphous reason is more is there, 20% crystalline is there, 20% highly oriented reason is there, and 60% amorphous reason is there. 60% amorphous is free space. The space is free is there. Okay. In this free space, that free space is amorphous reason. If the amorphous region is more, 60 is there, that amorphous region allow the moisture go into the structure. Outside atmospheric moisture is going and covering, accumulating that space. Outside moisture is entering into the fiber structure. If space is more, 60% amorphous is there, that 60% amorphous region is accumulated by the outside moisture, that is water particle, whatever you call vapor or whatever, is going inside. That moisture content is there. That moisture, if that 60% of the space of the fiber accumulated with the water particle or moist particle, then the weight of the fiber is increasing. The weight of the fiber is increasing. One point. Second point is the wet processing ability of the fiber is very, very good. Means it absorbs water, it absorbs dye particle, it absorbs other finishing chemical particles, and it will help to get the dye particle or finishing particle bond with the polymer chains. Okay, but don't think that 60% of the space is not, if it is there, that is not a good fiber. Usually what, as per my knowledge, as per my experience, what I studied, 12%, 5% moisture regain, usual properties are saying moisture regain percentage. That is come into the textile testing part, while go that separate class. 8%, 10%, 11%, maximum 16 or 2 maximum 20% is better. More than 20% is not good for the quality of the fiber or the product produced from that fiber. Okay. Wool is there. Wool moisture regain percentage is more, up to 13 to 16, 14 to 15, 16 is there. Cotton is also there, 11 something is there. But in case of synthetic fibers, because why the strength of the polyester fiber or strength of the nylon fiber is better than cotton fiber? Why? Because it's a man-made fiber. The man-made fiber, the industry, the filament producing industry is adjusting, modifying the morphology of the fiber while drawing the filament of the yarn in the industries. He wants highly oriented region in the nylon, so that the highly oriented regions gives strength to the fibers. Why strength of the nylon is more? Because the highly oriented regions in the fiber, in the morphology of nylon is more and less in polyester. And also why the shape of the nylon or polyester is synthetic fibers is more? It is modified. It is in the hand of the man. Okay, but in case of natural it is not there. The color, the luster of the fibers are shiny in case of nylon, in case of polyester. Why not in cotton? Why not in jute? Why not in hemp? Why not in silk? Silk shining is get after the finishing, but in the raw silk it is not shiny. Okay, the cotton, because the cotton shade, the naturally produced fiber is having 4 to 5 shades, it is giving grey, black, white, like that. Different is there because of the nature, because of this content production. All these polymers, naturally all this, the structure is produced in the cotton fibers or linen fibers, but that's naturally produced based on the cultivation, or based on the environmental, based on the what the area is there. It depends upon the area of the crop where it is done. Okay, understood the importance of the structures. In case of dyes, why dyes? Color first. One class already I raised, one class on small short class on color fastness of the fibers. Why color fastness is varying from fiber to fiber or color to color or dye to dye. Why reactive dye is more popular since many years recently than direct dye or wet dye or local dyes? Because reactive dyes, the name itself indicating the dye particle entering into the fiber and get bonded with the polymer chains, so that permanent linkage between the fiber and dye particle takes place in the reactive dyes. That is, the fiber and dye affinity is created more in case by the reactive dyes than direct or local dyes. For that also, to increase the dyeability of the fibers, not only color modification is not enough, but the fiber is also converted, mercerized fiber is required. Natural cotton fiber, if it is not mercerized, then the application of reactive dyes may not be efficient. May not, I am not saying 100% efficient, may or may not, because after mercerization, whatever the pores are there on the skin of the fibers, the amorphous region will open. The flattened cotton, the amorphous region is closed. If it is mercerized, the amorphous region will open like balloon, then there is a space will be there. The reactive dye particles or any dye particles going to enter and react with the polymer chains. Right? Mercerization is required. And also, why the cost of mercerized fibers or yarns is more? Because the additional process is required. Right? Tenacity. Okay, moisture regain is more. Tenacity, strength of the fibers. If highly oriented region is more, strength will be more. Whatever property, shrinkage also depends upon the moisture regain. And also see, the weight of the cotton is more when wet, or strength is more when wet. Strength is very less before, because this morphology. Okay, this morphology is influencing directly on the wet processing, finishing and quality of the fibers. Hope you have understood my presentation on this morphology of the fibers. Now I am closing this to make a half an hour video. Thank you. Please subscribe to my channel. Those who have not yet subscribed, please like it and share to your friends. Please click the icon bell to get my further videos in your mobile inbox. Thank you.